So we're going to talk about equilibrium, okay? Equilibrium is a dynamic situation, a dynamic state where we have a reversible reaction, okay? Reversible reactions are reactions that can proceed both in the forward direction, meaning we start with reactants, and some of it turns into product. But the product that gets made can interact again and reform or reproduce the reactants. So we actually have two reactions. They're reversible. We can go forward, we can go backwards. And equilibrium is the state where the rate of the forward reaction matches the rate of the reverse reaction. Now, for some reactions, they're product favored, meaning that the rate forward is greater than the rate in reverse, so you end up making a lot of product before you reach that state where there's an equal amount of reactant being reformed. And so we talk about a forward direction and a backwards or reverse reaction. And if we get a lot of product out of the reaction, then we say it's product favored, where the equilibrium lies to the, as we're going to see, lies to the right. And if it's reactant favored, that means that only a small amount of the reactant begins to disappear and form product until we get reactant reforming. And so the equilibrium, we say, lies to the left. Now, we can write this and express this mathematically based on either concentration or partial pressure if they're all gases. For any reversible reaction where we have two reactants becoming products, and each of them may have a coefficient to balance out the reaction, we can write the expression as an equilibrium expression. And this is based on something called the law of mass action. And what that law implies is that there is a proportionality of products to reactants when we're at equilibrium. And so if we know the concentration of each thing when it's at equilibrium, we can have a value called K. All right, big K, not little k. Little k we talked about with kinetics, and that was rate law. Here we're talking about equilibrium, which is big K. And that constant is a unitless number because it's just the proportionality. So for any reaction, the concentration of the products raised to the value of the coefficient in the equation divided by the product of the reactants, each raised to their coefficients, that tells us where the equilibrium is, a proportionality. Now, if that value for K is greater than 1, that means products are favored because the top part of this fraction would be bigger than the smaller part, the lower part, right? The numerator would be bigger than the denominator. And so that would be a product favored reaction, one where the equilibrium lies to the right. If, however, the K value is small, meaning it's less than 1, then that means that the denominator is bigger. There's more reactant present at equilibrium than product, which means that the equilibrium lies to the left, or it is reactant favored. Okay? Let's look at how we would write the expression. And this will become important later because if we know where the equilibrium lies in terms of what the K value is, we can then look at any scenario for that reaction and figure out whether we are not yet at equilibrium or are starting past equilibrium and need to go back to the equilibrium point, or whether we're already there and we're not going to see any new change in concentration. So if we look at the decomposition of nitrogen dioxide into nitrous oxide and oxygen gas, to write the equilibrium expression, it would be the products, so the nitrous oxide and the oxygen, each raised to their coefficients, divided by the concentration of the nitrogen dioxide raised to its coefficient. So then if we have numbers that we could put in there, we could have a value, a K value, that tells us where the equilibrium lies. And this will become very useful for us to look at in terms of acid-base behavior and in terms of other reversible reactions